Let's take a look at this example problem here. This problem here, we have a given diagram, and they tell us that we have a crate, you can see back here, with a mass M is being pulled by a cable right here attached to this truck, and we can see that the cable here in the diagram is coming up at 30 degrees off the horizontal there. They also tell us that the coefficient of kinetic friction between the crate and the road, right here, is our mu sub k. Now they want us to draw a free body and kinetic diagram for our crate right here. So our plan of attack for a problem like this is we're going to first define an inertial coordinate system. So we want to establish what is a positive x, what is a positive y. We could go with the standard y positive up, x positive right, Cartesian. We could say that y positive is down so we don't have to deal with negative gravity effects. We could say that x is positive to the left instead of the right so that we can put the coefficient of friction force in a positive direction. So we have different options, but if none of those jump right out at you as an easier way to solve the problem and to make things less complicated, then maybe stick with a standard Cartesian x to the right positive, y up positive coordinate system. Second, we want to draw the crate's free body diagram showing all the external forces applied to the crate in the proper directions. And lastly, we want to draw the crate's kinetic diagram showing the inertial force vector MA in the proper direction as well. So this, again, those directions there as we relate back to a coordinate system we choose as positive will make a difference on what's positive and what's negative in those two. So now that we've had the opportunity to go through the problem statement, understand what they're giving us, what they're asking for, and take a look at the diagram, the next thing we want to do is to create our setup page. So in this one here, see we have example 1 here, we have our diagram, the simplified version. There's my truck, my mass, my cable, my angle right there. Given to me is the mass of M here, and we have the coefficient of friction right there given as mu sub k. And we have this theta here, the angle off the horizontal of 30 degrees. Now, what are they asking us to solve for? Well, they want us to draw the free body diagram. So that's part of our solution, is drawing out the free body diagram and the kinetic diagram of the crate. So with this, establish a coordinate system, draw the crate's free body, draw the crate's kinetic diagram. So once we have all of our information from this front page, we can start with the coordinate system, then do our free body, then do our kinetic diagram. So let's take this solution step by step and the 3 different sections that we broke down our solution into. So the first step of our solution here was to establish an inertial XY frame that can be defined as fixed to the ground here. So that's our standard XY coordinate system. And as I'd mentioned as we were looking at the problem statement, unless something jumps out at you right away as a reason to change this, stick with your standard XY. So I have X positive to the right, Y positive coming up off the ground here. So now I want to look back at my given diagram and try to see every single force that is acting on our object that we're drawing the free body diagram of. So that's where it's great to have that first setup page so we can quickly go back to that diagram. So I'll do this here. Set up our initial diagram there. I can draw right below it here as I do my free body diagram. So the first thing I do is, okay, I want to draw out this box, this crate right here. So I draw that out as a square right there. Now I need to ask myself, okay, looking at this diagram and everything they tell me in the problem statement, what forces are acting on this crate? Well, I have my weight force from gravity acting right down here on it here. So this is my weight, which is equal to mass times the acceleration due to gravity, and it's acting down. So this is where this is acting in our negative y direction. So the sign convention of this weight force is going to be negative because we chose our y to be positive going up. What else is acting on this here? Well, we have our tension right here, a load being applied to this cable. So this is acting right here. I'm going to call this my tension force T, and I realize that this is acting up at 30 degrees from our horizontal. So this is not acting purely in the x or the y direction. It has a component in the x direction and a component in the y direction, which means I'm going to need to do some trigonometry over here. I'm going to need to break this down in terms of its x and y components, sine, cosines, tangents. So if I know this is at 30 off of my x, I can there go and find out, okay, what my x component is, my y component is, with some simple trig. So if they'd asked us to take this problem a step further and write out our equations of motions, we would need to break this tension force down in terms of our x and y components. Now, as a side note, if this was a problem of something being pulled up a ramp at this angle of 30, then maybe we wouldn't want to choose a standard Cartesian coordinate system here with the y positive up and the x positive to the right. Maybe we put this at an angle to the ramp where y is positive this way and x is positive up the ramp. So if this right here was being dragged up a ramp, then we might want to choose a different coordinate system. For our case here, it's just being dragged across the ground, and the only thing at an angle is this tension. So it's easy for us to just break this down in terms of x and y components than to try to get all these other forces into this coordinate system. So just something to think about as we're moving forward and we see some more advanced problems. So that deals with our weight force and our tension force. What other forces do we have? Well, we have a normal force. So what this is this is the force of the ground pushing back up at the crate. So there's our normal force right there, pushing back up at the ground. Then the last thing we have is a frictional force, which opposes the direction of motion. So the direction of motion, we're going in this way here. As the truck moves forward, pulling the box in that direction. The crate's moving in our positive x direction. So our frictional force is going to be moving in our acting in our negative x direction here. Friction is the force is equal to F, which is the coefficient of friction, or mu sub k, which is given to us, times this normal force there. So there's our frictional force there. So we have 4 external loads acting on our crate. Our weight force, components of our tension force, our frictional force, and our normal force. So our weight force and our normal force are purely in our y direction. Our frictional force is purely in our x direction. And our tension force has an x and a y component that we'll need trig to break down. So that is part 2. And kind of leading into if we had been asked to draw out our equations of motion. Part 3 is the kinetic diagram. So Newton's second law, force is equal to mass times acceleration. We're dealing with the right-hand side of Newton's second law here. Here's our mass times acceleration over here. So this is going in the direction of motion. So if we pull this up just a little bit here, so we can see a diagram here. Direction of motion, crate's moving to the right, accelerating, moving to the right, mass times acceleration, moving that direction. This is our kinetic diagram down here. Now, from our free body diagram and our kinetic diagram, that we could, if they asked us to take this one step further, say a summation of forces is equal to mass times acceleration, and we could start filling in all of our summation of forces in the x direction and y direction separately, and then all of our kinetic information from our kinetic diagram on the right hand side of the equation here for Newton's second law.